what we talked about so far is that matter has volume, it has mass, it's made up of substances, elements, and compounds. We have the periodic table, it tells us which elements we deal with. We want to know what defines an element. Right? So if I have a certain element like lead or carbon or something like that, what defines that? What makes it different from the other elements on the periodic table? And the answer to that is the number of protons. So to be an atom, a particle has to have at least one proton. If you just have a neutron flying around, that's not an atom. It's just a neutron. If you have an electron, like the beam of electrons in the cathode ray experiment, those are not atoms. Right? They're smaller than atoms. But to be an atom, there's got to be at least one proton. Does an atom require the presence of a neutron? No. Does an atom require the presence of an electron?
Yes.
No. All an atom requires is one proton. That's really what most hydrogens are. Hydrogen has a mass of 1. That means there's one massive particle in hydrogen. The massive particles in atoms are either protons or neutrons. The electrons don't have much mass to speak of. And if there's only one massive particle there, it can't have both a proton and a neutron. It just has one proton. That's all a hydrogen is. Now, that proton is positively charged, so it attracts electrons, and it might be in the room or if there's a hydrogen on the molecule in your body, it's attracting electrons. It has electrons around it. So most hydrogens have electrons. But there are lots of examples where you have a hydrogen atom that might be associated with some electrons. You can knock the electrons out of it. And that's just a proton. It's still an atom. It's still a hydrogen atom. Okay, so the bare minimum to make an atom is one proton. That's what defines hydrogen. It is defined as one proton. And so then if we look at the periodic table as we go to the next element, helium, it has 2 protons. Then the next element has 3. Every element has its own specific number of protons. That's what defines an element. You cannot have a lithium atom with more or less than 3 protons, because what defines lithium is having 3 protons in the atom. So let's talk about the early experiments then. We'll add a couple more details that maybe we didn't mention initially. So the cathode ray tube is actually a really pretty simple experiment. The ideas behind, the theme behind these experiments is scientists wanted to know what's in atoms, what's in matter. So their idea was, let's try to take these chunks of matter and break them down into pieces and see what the pieces are that are present in that matter. Right? So, and physicists and chemists are still doing this. We now understand protons, neutrons, and electrons, but what are those made up of? If we break those into smaller pieces, that requires a huge amount of energy, so you need those super colliders. But we want to understand what makes those up and how that works. We have to break those down into smaller pieces.
Do you have success doing that?
Yeah, there's a lot of success doing that. But that's a little outside of the scope of what we need to talk about. So we're going to focus on the more basic protons, neutrons, and electrons. So the cathode ray experiment basically just comes down to understanding and characterizing electrons. Right? So if we know matter is made up of particles, what they did in this experiment was to strip the electrons off of those particles. Right? So most atoms have electrons associated with their nucleus. And so if you create an electrical potential, like we saw in that video, where one side is negative, what we're basically doing is all the matter that was in that battery or in that electricity source, all that matter has electrons associated with it, and we're causing the electrons to be stripped off and build up here. If I build up enough electrons here, by stripping them off of atoms, that creates a bunch of extra negative charge. And so basically we're just taking the electrons out of atoms and looking at how they behave. What are their properties? And so building up that negative charge here, if we have a positive plate here with a hole in it, the negative charge, eventually when we build up enough of it, it will be so attracted to that positive and so repelled by the other negatives on this end, it will shoot toward that hole and come through the other side. Now if I don't include this magnet, it'll just shoot straight through. But this magnet with the north and south pole also shows we're characterizing what the properties of these electrons are, and they have the ability to attract the magnets. So some of the, well, depending on where you put the magnet, one side of the magnet's presence will push the electrons up here, the other side of the magnet's presence will push electrons down there. So that video does a better job of showing that. So maybe I'll just pop that on real quick since we didn't get to see that part.
Is traveling to the other end of the tube.
So there's no magnet
When the ray
here.
strikes this specially coated surface, the cathode ray produces a strong fluorescence or bright light. When an electric field is applied across the cathode ray tube, the cathode ray is attracted by the plate-bearing positive charges. Therefore, a cathode ray must consist of negatively charged particles. We know these negatively charged particles as electrons. A moving charged body behaves like a tiny magnet, and it can interact with an external magnetic field. The electrons are deflected by the magnetic field. As expected, when the direction of the external magnetic field is reversed, the beam of electrons is deflected in the opposite direction.
Yeah, this was...
In 1897, J.J. Thomson, an English
This
is
was
attracted by the plate-bearing
electrical charge. So we know that electrons are negatively charged because of their attraction to the positively charged plate. We also know that electrons have magnetic properties. And finally, what they did was to adjust the electrical field here. So if we know how much positive charge is here, we can quantify that with a number, and we can calculate the angle here that these are disturbed from the normal straight path. We can calculate that angle. We know how much charge is here. We can use some calculations, which I'm not going to expect you to do. But we can use some calculations to actually calculate how much negative charge is on an electron. Right, so the bottom line of the cathode ray experiment is we're stripping electrons off of atoms, showing that matter, some of the particles in matter have negative charges. Right? So that's really the bare bones of it. Some matter, some of the particles that make up matter have negative charges. And we can quantify the quantity of negative charge. We can show exactly how much negative charge an electron has. So that is the cathode ray experiment. And the amount of charge on an electron, not on this slide for some reason. I thought it was there. Oh, well, they had the charge to mass ratio, is actually what they calculated. So a coulomb, this capital C stands for coulomb, that's the metric or systematic unit for charge, the quantity of charge. And so one electron has a certain amount of charge, but if I had a gram of electrons, that's the amount of charge we would have. Right? So now we know how much charge there is on an electron or how much charge there is on a lot of electrons, enough electrons to make up a gram, based on that angle and how much charge caused the electrons to be having their trajectory disturbed at that angle. Right, so that's the information that scientists got from the cathode ray experiment. Any questions about that? Okay. Also, Rankin and others studied X-rays a lot. At the time, you know how dangerous these high energy forms of radiation were, but X-rays were not shown to be deflected by magnetic or electric fields. Right? So that suggests that when matter is high in energy or unstable or radioactive, like radioactive nucleus is radioactive because it's unstable. When the nucleus undergoes a change to become more stable, some energy is released. We'll talk more about energy later, but sometimes the energy is a high energy form of light, like gamma rays or X-rays. And those are forms of energy. They are not forms of matter. Okay, so separate from the cathode ray experiment, there are other experiments that show that matter can release these forms of light. They're not charged. They don't have mass. They're just energy being emitted from the atom. So that tells us that for an element, there's more than one way to arrange it with different degrees of stability. It can be stable and not release this energy, or it could start off unstable and rearrange itself and in the process release energy. So then another experiment that looked at what's in matter is to look at something that's radioactive. So if we have an element that's unstable in its nucleus, it will naturally break up its nucleus and release things. So if we want to know what is the atom's nucleus made up of, we can take some of these elements that are naturally radioactive, that are naturally breaking up constantly and releasing stuff, and look at what's released. So we take that matter that can release things, put it inside a box, focus its beam. We can use charged plates to see if the stuff coming out of the atom is charged. Yes?
The lead block is just to keep it neutral so it won't escape.
Yeah, the lead block is just the lead is dense so that the radiation won't go through the block and it will only be able to escape in one direction. So then this stuff coming out of the atom as it breaks up passes through here, and we see it's made up of different types of things. So for this particular element in its unstable state, it has the ability to release, or is releasing, things that are negative because they're attracted to the positive plate, things that are positive because they're attracted to the negative plate, and energy that's not charged and has no mass. So they can characterize what's coming out of here and look at its properties. Again, depending on how much charge there is on this plate and the angle of deflection, they can say something about these particles, how much charge they have and how heavy they are. And so they discovered that the alpha particles have a mass of 4 AMU. If you recall, when we talked about AMU, we said an AMU is the mass of 1 proton or 1 neutron. So this is the equivalent of 2 protons and 2 neutrons. It's really the same as a helium atom's nucleus. That's what an alpha particle is. So we've got these 4 particles, 2 protons, 2 neutrons, stuck together, flying through space. That's what an alpha particle is. Right? So that means that whatever this radioactive material was inside that lead box, it's unstable, and it has to release some of its protons and neutrons from its nucleus in order to become more stable, and that's why they're flying out, and that's why they're attracted to the negatively charged plate. The beta particles were found to have the same angle of deflection as the particles in the cathode ray tube. So this tells me that beta particles are electrons. They have the same mass to charge ratio as the electrons in the cathode ray tube. They're the same substance. So the cathode ray tube showed that you can strip electrons off of atoms. This experiment shows that some materials that are radioactive will just emit electrons. Naturally, their electrons are somehow making them less stable, and when they get rid of them, it becomes more stable. So those electrons are just naturally given off over time. Yes?
The electronic charge plates separates or makes whatever which one's stronger in the direction the rays becomes, beta, alpha.
So these charged plates are what is attracting, since the electrons are negative, as they move through here, they feel an attraction to this positive plate that pulls them up. So instead of going straight, they get pulled up at an angle. Is that what you're asking?
It gets pulled up at an angle and it goes down. That's what it's showing. It could go separate directions.
Yeah, because the alpha particles have protons and they're positive overall. The positive charge, as they come out, they get attracted to the negative plate, and that pulls their angle down. And since the gamma rays are just a form of light, they're not particles and they don't have any charge, they just go straight through. All right, so again, pretty basic experiment. You all already knew that there are protons that have a positive charge in atoms and there are electrons that have a negative charge in atoms. When these experiments were done, they didn't know that. Right? So they're trying to figure out what is in matter by breaking the pieces of matter apart and looking at the pieces that come out, characterizing those pieces. And we talked about the Rutherford Gold experiment. Any questions about that? Yes?
I have a question not about that.
Sure.
The difference between gamma rays and X-rays, can you clarify?
Yeah, that's a great question. The difference between gamma rays and X-rays. So gamma rays and X-rays they're just really forms of light. So there are other forms of light. There are microwaves, radio waves, infrared, there's visible light, there's ultraviolet light. The difference between those forms of light, the only difference between them is how much energy they have based on how long of a wavelength they have. So when we think about light, we think about it as being like a wave. Right? So if I'm standing here outside and it's a nice sunny day and I'm smiling, the light is hitting me and that feels nice. Especially on a little cool day, it's nice to be in the sun, right? The sun is giving off lots of different types of light, including really pretty much all the different types of light in the spectrum. But maybe this wave represents visible light. I can think of each wave as being like a packet of energy. So when the wavelength is long, I'm not getting hit by that much energy. And that's good. I mean, I like to get warmed up by the sun. It feels nice. I want to get hit by some energy. And all light has some energy. But the longer the wavelength, the less energy there is because the packets are kind of spread out. So gamma rays are the highest energy form. They have extremely short wavelengths. The distance between these packets of energy and a gamma ray are like picometers, which is like 10 to the negative 12th meters. They're like super, super tightly packed. You don't want to get hit by a lot of gamma rays because there's just a little bit of a gamma ray packs in a huge amount of energy, and that energy is concentrated into whatever part of your body it's hitting. It can cause, your molecules to break up. It can knock electrons out of the bonds that are holding the atoms together. It can break down your tissues, and it can, cause DNA to mutate, things like that. So on the high energy end, where I have a low wavelength or a short wavelength, because the energy packets are packed really close together, I've got gamma rays and X-rays, and we want to limit our exposure to those because they're damaging because they have so much energy. After that, you've got UV, you've got visible. You also want to limit UV. I mean, the UV isn't as dangerous, but over time it can mutate your DNA and break up the structure of your molecules. The energy can break those molecules up. And then you've got visible and IR and microwaves and then radio waves. And these, as we go from left to right, they become less and less dangerous. Yes?
Since gamma ray has no charge, why would they have such a strong energy?
So they're different forms of energy. If you're thinking about the energy associated with a charge, the energy associated with a charge is like the potential for that charge to attract to another charge. Light isn't attracted to charges, but it still has a different type of energy kind of held within it in these packets of energy. So when you get hit by light, it's not really affecting the charges, but it's like getting hit. It's like getting physically hit by something that's hard. Right? So if somebody hits you really hard, it could break a bone, it could do some physical damage to you. Likewise, if you have like an atom with electrons around it, if a beam of light comes in and hits those electrons, it'll just knock the electrons right out of the atom. And that changes the properties of the atom. It doesn't necessarily do that based on the charge. It's not like it's coming in with a positive charge and attracting the electron and pulling it out. It's just like, you can think of it as kind of like physically hitting that electron and pushing it away. So the higher the form of light, the more likely it is, the higher the energy, like gamma rays and X-rays, really high energy, the more likely it is to distort molecules and push electrons out and break things up.
When you say light, shouldn't it be invisible? As in, for certain types of gamma rays, require a Geiger counter?
So all of these forms of light are invisible except visible light. So to detect that light, you need some type of instrumentation. In the experiments where they were working on it, they had usually something fluorescent on this screen. So there are some molecules that when they get hit by energy, that they absorb that energy, and then they later re-emit that energy in the form of light. So the screen will light up in areas where the energy is hitting it. There are other ways to detect light using electronics and things. So you don't have to actually physically see the light with your eyes to know that, to be able to detect its presence. All right, so I wanted to talk about this just for a few minutes. Why do you think gold was used in the Rutherford gold experiment? Why not some other material?
Gold is not reactive, hardly.
Yeah, that's one really good point. So let's talk about this question here. One is that it is pretty inert or stable. That's one advantage of gold. Right? So the idea here, the whole point of using this foil was what? To set up a barrier. To see if these particles would be deflected by the barrier or if they would pass through the barrier. We didn't want the particles to come in and stick to the barrier or change the structure of the barrier. That's just another variable we didn't want to have to worry about. Or I shouldn't say we. I wasn't involved in it. But the gold, among metals, gold is like the most inert. Gold is very stable. That's why it's good for jewelry, right? You have a gold ring, you keep it for years and years, decades, centuries. It's still nice. It looks shiny. It still keeps its color. It doesn't rust. It doesn't corrode, right? Because gold, as an atom, holds its electrons in tightly. It's very stable with its structure. So since it's a stable individual atom, if alpha particles coming in, it's not going to pull electrons out of that atom. It's not going to knock the atom apart or affect the atom. It's just acting as a barrier to see if the alpha particle comes in and gets repelled back, or if it makes it through the gaps between the nuclei of the gold atom. That's the main reason. Any other reasons why gold is a nice substance to use in this experiment that you guys can think of?
Isn't gold highly conductive?
It is conductive, so in this case that's not super relevant because since our alpha particles are positively charged, we don't have to worry about electricity really being involved. If we had like a flow of electrons, then that might be an issue to conduct a flow of those electrons across the gold metal. Another advantage of gold, though, is that it's very soft. And so if you have gold jewelry, it's very unlikely that your jewelry is pure gold because it would be soft. It would be easy to bend and mold that structure. And other metals are mixed in to make it harder so it doesn't get distorted or bend. But you can make a very thin sheet of gold foil because if it's pure gold, it is very soft. And so they were able to make a very thin sheet because of the softness and the malleability of the gold. Any other reason why you could think gold might be helpful in this experiment? I should be writing these down. Soft. Yeah, the other reason has to do with its density, which has to do with the size of the nucleus. Right, so the idea here was we don't want to use some small atom because if I use like a small atom like carbon, which doesn't have very many protons and neutrons in its nucleus, if it only had a few protons and neutrons, then if they were spread out or if they were packed into a nucleus, the alpha particles might make it through either way because the nucleus isn't big enough to really deflect it. So the idea with gold is because it's close to the bottom of the periodic table, it's got 79 protons in its nucleus and lots of neutrons. That creates this pretty big atom compared to the size of the alpha particle, which is only 4 protons and neutrons. 4 protons and neutrons versus almost 100, that's big enough where if the particles in the gold were really spread out like the plum pudding model, then the alpha particles could make it through. But if the particles in the gold were held in a nucleus, there are so many of them that when the alpha particle comes in, it should have a decent chance of being deflected. So the size of the nucleus was another key reason why it makes a good substance to shine these alpha particles at to see if they get deflected. So as I said, as the alpha particles were deflected, the number that made it through the empty spaces between the nuclei. The ones that were deflected were approaching the nuclei and their positive charge got repelled by the positive charge in the gold nucleus. And then they were able to calculate, based on how many made it through versus how many were deflected, exactly how big the nucleus was. 5.3 times 10 to the minus third picometer. A picometer is already 10 to the negative 12th meter. I don't know about you, but I cannot imagine something that small. My brain is not capable of thinking of things that size. Because I'm a visual person, I'm thinking, what's the smallest thing I can imagine is, well, that's the smallest thing I could see, like a speck. Something smaller than a speck, I don't know, I can't see it. I can't imagine how small that is. But 10 to the minus third picometers, that's like, I don't know, it's really small. So, whatever. Super small thing. The size of the, just to point out though, the size of the nucleus relative to the size of the atom, it's a big difference. 5 times 10 to the minus third picometers versus 100 picometers. That means that based on how many alpha particles are making it through there, that suggests that the size of the atom is way more than the size of the nucleus. So when you think about an atom, you might think about like representations on television and things where they show like, you know, the nucleus and then the electrons like this, you know, like compared to the nucleus. That's not right. The nucleus is like too small to see compared to how big the atom is overall, and that's why this picture I think is so great, because it shows the nucleus relative to the size of the atom. So if I zoom in on the atom until the atom's this big, the nucleus is still almost too small to see because so much of that matter is packed in the nucleus. Why is that true? Why is there so much matter in the nucleus? Why would all the protons and neutrons be stuck together in this tiny, tiny space with almost nothing around it? Why wouldn't they spread out? I mean, if you think about it, the plum pudding model makes more sense. The plum pudding model suggested that, it was their hypothesis, that all these protons and neutrons weren't in the center, but they were spread out. Especially the protons. The protons are all positively charged. Positive charges repel one another. Why are they going to get super close together in the nucleus? Have you ever thought about that?
The building blocks hold it together.
Yeah, I mean, there must be something holding it together. Something other than charge attraction. Right? So what are the forces that affect matter in the universe? There's gravity. Gravity works on large-scale things. It's a distortion of space-time. We also know electrostatics. That's just normal attraction between opposite charges and repulsion between like charges. Neither of those forces can explain why the nucleus is stuck together and why all the positively charged protons get close together in the nucleus. What other forces do we know of? There's a nuclear force. There's magnetism. Right? So there's really 4 big forces. One of the 4 main forces that are governing the universe is the nuclear force. It's called the strong force. It's called the strong force because it's the force that holds the nucleus together. It's just a fundamental force. We see that the nucleus exists. We know that these particles are stuck together. There must be a force holding it together. Let's call it the nuclear force, or let's call it the strong force. We just need a name for it. So that means that there are attractions, some type of attractions between these particles in the nucleus. It's not a charge attraction. It's not a magnetic attraction. It's not a gravitational attraction. It's a different type. It's a specific, it's its own type of attractive force. Any questions about that?
Yeah, I think we skipped the question why alpha particle radius.
Yeah, so that was what I wrote here at the top right. Because, why are alpha particles here? Oh, yeah. Yeah, well, the alpha particles were used, that's a good point, I did skip that over. So, in the Rutherford-Gold experiment, the alpha particles were used because there are only so many types of radiation. Right? The most common types of radiation are alpha particles, beta particles, and gamma rays. The gamma rays shouldn't be used because they're not even particles. So the idea here is if we shine something in here and it goes through versus if it's deflected, that will tell us how this matter is arranged. So we need something that could possibly be deflected. So it's down to like beta particles versus alpha particles. The beta particles are really small. They have like way less mass than the alpha particles. And they're negatively charged. So if the beta particles come in, they can get stuck in there and get attracted to the nucleus. So the alpha particles were the best choice because they give us the best shot at just seeing that as a barrier possibly to see if the alpha particles just physically make it through or not.